Hello.
Hello, am I audible?
Ye- Yes, Bapi Chaterji, sir, you are audible.
Okay.
Sir, just wanted to test audio. I hope everybody is getting voice from my side as well.
Yes, sir.
Okay, okay. Thank you so
Yes,
much.
sir.
Clear, sir. Clear, sir.
Okay, so I hope my screen is also visible.
Sanjana, you can start the introduction of Professor Bapi. Sanjana, can you hear me? Hello, Sanjana, can you hear me?
I can hear you.
Sir, just a second. I'm just informing to Sanjana and Pradney.
Sanjana, can you hear me? Unmute you.
Sir, they are about to start. Just give us 2 seconds more.
Sir, I can hear your voice clearly.
Yeah, Sanjana, start the introduction of Professor Bapi, please.
Okay, sure, sir. Good evening, everyone. Welcome back to day two of our event, FDP, Faculty Development Program, Generative AI Techniques, Tools, and Application. I hope you all are as excited as I am today, filled with learning and inspiration. Without further ado, let's jump into today's conversation. Now it's my honor to introduce our first keynote speaker of the day, Dr. Bapi Chaterji. They will enlighten us on training the generative modeling. Dr. Bapi Chatterjee is an assistant professor in the Department of Computer Science and Engineering at the Indian Institute of Information Technology, Delhi, IIIT Delhi. He leads the and Learning Lab at IIIT Delhi, focusing on advancing research in distributed machine learning, concurrent data structure, and architecture search, and learn index structure. Prior to joining IIIT Delhi, Dr. Bapi Chatterjee also served as an IST Plus postdoctoral fellow at the Institute of Science and Technology, Austria, collaborating with esteemed researchers in the field before his postdoctoral venture. He was a research staff member at IBM India Research Lab in New Delhi. Dr. Bapi Chatterjee earned his PhD in computer science and engineering from Karl's University of Technology, Gutenberg, Sweden in January 2018. Dr. Chatterjee's research interest encompasses a range of within computer science and mathematics, including distributive machine learning, federated learning, concurrent data structure, learned index structure, parallel programming, GPU, blockchain, computational topology, and computational game theory. His work has been published in reputable conferences and journals, contributing to the advancement of this field. In addition to this research, Dr. Bapi Chatterjee is dedicated to teaching and such as optimization method for machine learning, concurrent and learned data structure, discrete mathematics, distributed learning and object-oriented program and designed at IIIT Delhi. His commitment to education and research continued to inspire students and colleagues alike. Let's give him a big round of virtual applause. Now take the stage, sir.
Okay, thank you for the intro. I am so I'm very happy to join this session and to speak with all of you. So let me first shake. So first of all, my camera is not on, but I believe that should be fine. My mic, I kind of sense that it is working because otherwise, yeah. So it was already tested. So my screen that I shared, the slides, I hope that is also visible.
Yes, sir, it's visible.
Okay, perfect. All right. So then let's start with this session. And thanks for the introduction again. Like it was mentioned that I work on distributed machine learning. Uh, so today I'm going to talk about training large scale models, right? So this, uh, the topic that we are going to discuss lies at the foundation of today's let's say generative AI, right? The big models that are being trained and deployed, and then we are always sort of awestruck with every new development. So let's see the developments that I just said. So here are some frontier AI models this month, right? So this is sort of the latest developments that happened over maybe just last week, right? So all of us, heard about uh, DeepSeek's release, and thereby we also got to know that China is now a big player in AI, and they are giving very big competition to US-based OpenAI and so forth, right? So these are like some big players, in particular Google, and then Google's Gemini, and then GPT-O series of models from OpenAI. So in general, I mean, when you have these big models, the way we use them is something like you use that either on on a laptop maybe, or on a mobile phone, right? So that is like like interface to do inference of these models. But we don't realize that what would have gone into the training part. Some more data here to, I hope it doesn't overwhelm you, but let's see. So here are some models with their GPQA. So GPQA is a benchmark, right? So whenever a new model sort of comes in the market, uh, people uh, have to give, so those models as they are released, they have to give this data right out for people to know that, okay, how effective their model is. So of course, OpenAI is, this O1 model, which was released in December 24. They sort of performed 92.3%. So I mean, it's not, don't go by percentage, but just know that it is a score. Okay. So this model sort of achieved 92.3, and then they said that, okay, it actually used billions of money and so forth. We will see that also. I mean, I have some data collected, but then DeepSeek, which was released in January 25, it scored almost as well, right, as OpenAI's O1, just a little bit lower, but it used very substantially cheaper budget, right? And there are other models, that appeared again. Well, I mean, last month we heard about, everyone heard about this DeepSeek R1, right? I believe that many of you have already tested it. But at the same time, some other models were also, released. For example, this Rubik's AI. This is also another big, company from USA, and their model also performs very competitive to DeepSeek R1. And there are many others. So, but you see, I mean, all these models that we see on this list, right? They are either from China, CN, or from US. Anyway, so there is a big ongoing competition in the market of model, and that competition is as fierce as this. Okay, so here is the data from last year, right? The number of LLMs released per month. Okay, so you can see that so this is like a very interesting plot, or let's say piece of information. So this red line shows you that how many hours did it take for a new large language model to get released in a particular month. So for example, let's say in December last year, there were 20 such models released. So roughly it took like 38 hours, before a new model came in the market, right? So this is like so fierce the development is in this domain. And similarly for derivatives, right? So these are like major models. So here you can see major models, and here you have derivatives. So derivatives are the one. So I don't know, maybe some of you would have heard about this news that this DeepSeek R1 actually used some data and maybe distilled the model, right? OpenAI so one model. No one has any proof, but people kind of guess it. Regardless, I mean, the idea is that people build newer models from let's say a better running model, right? Uh, another idea in this domain is derivative. Derivative is something like you take a big model and then you sort of specialize that in some domain, right? That becomes a derivative of the same model. So again, in that sort of sector as well, there are very big developments. So you can see how many derivatives every month, month by month, that came out last year. So for example, in December itself, there were 9,000. In May, there were 15,000 derivatives that came out in the market. Okay. So so again, so here you can see the money that that is claimed to have been spent, right, on developing these models, and then the number of GPUs that have been used, right, for such training. So you see the numbers here. So for example, this GPT-5 used something around 50,000 800 GPUs, right? So this is like a huge. So I don't know. I mean, I can I can mention here some piece of information that I stumbled on recently. That by the way, now this restriction on NVIDIA chip export from US, right, is sort of such that India cannot buy more than 50,000. I believe this the latest one. It's not definitely 800. It's a bit more advanced than the 800 chips. But India has permission to buy only up to 50,000. And you see, these companies, right, OpenAI and so forth, they are using these many GPUs, and that also, so you can see that it is like 50,000 GPUs, and that ran for 120 days straight, right, to train this GPT-5 model. Although I'm not sure if this is already in the market, but that's the kind of a story, right? And then equivalently, the total time that it took was something like 16,438 years, and this much money was spent. So well, I mean, what I'm trying to do is that I'm trying to give you a perspective of sort of how important this area has become. In particular, my focus is on training, right? I'm not talking about so many different things. Maybe yesterday you would have sort of heard about LLMs, and then SLMs are perhaps as relevant as LLMs, right? From Tanmoy, I'm not sure though, but I saw that on the schedule. Anyhow, so there are so many different things, but at the end, those aspects are mostly inference based. Here my sort of context is, or scope of this particular talk is training the models, right? So that should be very clear to all of us. Okay. uh, final piece of information here. So you can see the number of tokens that have gone into training these models, right? So you saw the model size first of all, and then here you have the token size, right? So what happens is that all these are like big data sets, right? So people develop these data sets, and then and then new LLMs train themselves over these data sets. Some of them I believe are maybe accessible, to public, but many others are not, right? So here you can see something like 9,000 trillion tokens are there in this Cosmos data set that is released by NVIDIA, and similarly for other, search. Okay, so having given you the perspective, now let's get back to the actual stuff, right? To the actual learning stuff. I mean, this is all piece of news, right? This looks good, but how exactly we can reach up to there? That's the question. And in particular, I believe that coming that this gathering is of people coming from academia, right? I must say something about the basic things, the fundamental things. Okay. So I'm pretty sure that up until here, maybe it was all about information, but still I must check that any question, if there is any question. Okay. So the way it will work is that maybe Sanjana, who is moderating the session, right? Uh, so so you can unmute yourself as you see any question coming on the chat. Please unmute yourself, and then please feel free to stop me. I mean, yeah, it will be good that if you sort of stop me wherever there is a collection of like 2-3 questions, because doing this presentation online, I have to mostly see on my slides, right? And I don't exactly read the chat that is coming up. Okay, all right. So here is the machine learning ecosystem. So essentially you have this training part, right, where you have training data and then model, right? And then you train the model on a bigger machine. I mean, although it is in this representative image, uh, I have only one maybe GPU and one machine, but in essence, this is like a cluster, right? This is actually a supercomputer, which is a cluster of several multi GPU machines. Okay. Once the model is trained, then you take that model to a smaller machines and do inference. So, like I said, that it is about training, right? That we are going to discuss in this session. So we have a model, right, and then we have training data. Let me use some mathematical notation here to make this discussion a bit more formal, right? So we represent a model by a vector, right? A d-dimensional vector. I believe that all of you have at least, a very basic background in linear algebra, right? And so again, this particular discussion will require very, very basic. In fact, just first introductory courses in linear algebra, maybe vector calculus, in particular the gradients, right? And yeah, and I believe not much in probability, but linear algebra and vector calculus, or multivariable calculus as we know it. So, so the it is this particular algorithm, stochastic gradient descent. I believe again, maybe all of you have heard of it, right? Stochastic gradient descent, or SGD, as it is called more popularly, is sort of now accepted as a workhorse of training the models, right? Training the machine learning models. So idea is very simple. You have a model, right? Machine learning model, which is essentially a vector, a d-dimensional real vector, and then you have training data. Let's represent that training data as this big S, set of big S, right? And every sample from this set will be represented by little s. Okay. Now, with that, we learn this SGD process. The idea is that we compute a gradient, right? Essentially, this is so this is gradient, and with gradient, the base algorithm is just gradient descent or gradient descent. It becomes stochastic here because what we do is that we actually sample a mini batch from this this data set S, right? So big S is our data set, and then we are picking a picking a subset from this set, right? So this is like sampled with some kind of a distribution, and that sampling brings in stochasticity, right? So thereby it becomes SGD, stochastic gradient descent. So this gradient, nabla, we call it nabla fx, is a stochastic gradient of the of the function. So this function is this function f is function of our data b, right, and our model x. Okay. In essence, in a supervised learning setup, what we do is that we have to minimize the empirical loss. So I mean, I believe that many a time what happens is that we face this question, or rather we ask this question to students. Maybe I can share you my experience, right? So people come here, the students in particular, right, and come here for PhD admission, and then all of them these days want to do something in machine learning, right? So I want to do a PhD in machine learning. All right. So what is training? So everyone would say that, okay, training is you have a model. They don't even say many a time model, just neural network, and then you update it. And then how do you exactly update that? Well, I mean, there perhaps many of them fumble. So idea is that we do empirical loss minimization. Empirical loss is essentially, the difference, rather the distance, some kind of distance, right, between the observed. Let me use function O for that observation, right, using the model and the data, right, and the actual, sort of. Well, I mean, I should not use I there because it is for the model. Wait a second. So I should not use I, but what I should do is that I will be using YB, right? So YB indicates the true labels of the data, right? So B is our data and YB is the label. So true label. So for example, cat, an image and its label is YB. So this empirical loss F is essentially FXB is essentially this kind of a function, right? So where output from the model, and you compare that with its level, and then it's some kind of norm distance is the loss function, empirical loss function. Once we have that, this function is well defined. I mean, of course, this is like mean square loss, but for training a neural network, we use so many types of different loss: negative loss likelihood, negative log likelihood, and cross entropy, and so forth, right? But without going into the specificities of those loss functions, here I am treating them as a generic function. This function is denoted by f. Okay. Once we have the stochastic gradient, right, of the loss function, all that we need to do is to update the model, right? So model will be updated from the previous state, which was x. Now, we do minus nabla f of x comma b, right? So where b is the mini batch, stochastic mini batch, and that way the model is updated. This is called optimization process, right? So essentially, we are minimizing here. We are minimizing the function fx, over this data s, right? Data s. So let me write fxs rather here, and x just belongs to rd. So we need to find that state of the model, which would minimize the value of it. Okay. This alpha here is called learning rate, right? Learning rate is kind of a dampening factor. Very often this alpha is between 0 and 1, right? Because it has to be a dampening factor. And then this update procedure, we just iterate. And I believe that this is perhaps one good point where I should ask if there is any question.
So there is one question in the chat which I would like to read out to you.
Yeah.
So what are the key factors to consider when selecting a data set for training generative models effectively? This has been asked by Dr. Rajesh Kumar Kanwar.
Okay, very good. I mean, let me ask, let me rather ask this question, and then perhaps it will give you some idea. Suppose you have a data of I don't know, one maybe images, right? And suppose you have so many overlapping images, so maybe you have 1,000 images and 500 of them are similar, right? Or exactly the same. Do you think that that data will be useful, or maybe if you just have maybe, I don't know, 550 such images and then all of them are distinct, right? So I believe that your natural answer will be the one that has different images. So data should have so this answer more formally should be answered from information theory perspective. Your data should have lots of entropy. Okay. So how to have a higher entropy? So well, I mean, entropy is something like a measure of information. A data set that has higher entropy, or that has higher let's say diversity in its samples, that's a good data. Okay. What people do in general is that even if you have, let's say, small amount data, you use some kind of process to generate synthetic data so that you could have diversity. Very simple thing is that you do, so for example, let's say you have an image, right? So you just rotate that image to create a new image, and that will sort of give a new let's say a new sample to your model training process, right? So these are like techniques. So of course a data which has lots of diversity is a good data. And so maybe if I could give you some more info here. So what is happening is that these days, right, as scrappers, so to say, right? Those software that which are collecting data for training these big models, big generative models, right? So they are ending up collecting the data generated by the models themselves. So, for example, let's say now you have to build a new LLM, right? Maybe if you just collect the web pages, right, as text, a lot of them has actually text which are already generated by other LLMs. So this data has a lot of similarity, and therefore the data quality has become a big issue. The bottom line is that you should have good diversity in the data, thereby you have higher entropy. Okay, how to address the issue of overfitting in generative models, especially when working with limited data? Very good question. Well, I mean overfitting uh, sort of so the idea is that okay, what is overfitting? Well, I mean, we understand that it has to be something like the training loss becomes zero, right? So the classical thing to solve this issue is regularization, right? Regularizer is like a function. So essentially what you do is that you introduce one term in your, so if suppose your original loss function is fxs, right? So you introduce a term, maybe lambda by 2 nabla of x minus some x square, something like that, xi square, something like that. So with respect to every data sample, you introduce one regularizer. This is the classical approach. So the way it works is that, okay, it doesn't let this if you have sort of good tuning of this parameter, it doesn't let this f to become zero, right? So if this f doesn't become zero, if empirical loss does not become zero over your data, then it is not an overfitting. But otherwise, yes, I mean, as soon as you have a number of parameters becoming larger than the number of data samples, overfitting is a possibility. I don't know if that answered your question. Limited data, again, if you have a small data, I mean, that is just not enough, as it is said, right? The data has become a big issue as we are so many people in India, many academic setups as well as industrial setups, as they are exploring how to build some LLM from India, data is becoming an issue. Okay. Then what methods can be used to evaluate the suitability of a data set before using it for generative model training? Well, again, like I said, that so it should have high entropy. So
उन्हें कुछ
maybe
पता तो रहता
one
नहीं होगा वो करते हैं, कोई उन्हें बहुत अच्छा पता होता हो, जैसे वो जानते हो तो
So there was some intervention. Can you please come again? Okay, never mind. So please don't unmute yourself unless you have, something to ask. Okay, cool. So yes, Rajesh had asked, how do we ensure ethical? Okay, I come to that. But before that, what methods can be used to evaluate the suitability for a data set before using it for generative model training? Good question, right? So let me give you my perspective. Look, so these days, what is happening is that a lot of brute force is happening. I mean, we just saw this piece of information that millions, even billions of dollars are being invested. The other day, there was an announcement from the new U.S. government that they are going to set up a $500 billion Stargate project, right? And sort of which will which will take the AI to AGI and so forth. But at the end of the day, a lot of brute force is happening. People don't, clean up data. A lot of redundancy is there, right, in data. One area of research which I explore, right, recently we submitted a paper, is called core set. Okay, so core set is, so core set, let me write it over here. Okay, you can maybe later check out about it on Google. But idea of core set is very simple. So suppose you have this data is, like I said, that there would be a lot of redundancy, and maybe some of the data samples will not actually benefit your model training. In particular, some of the data samples, let's say some SIs, right, as we collect them and try to compute this nabla f, right, this gradient is sort of very close to zero maybe, or this gradient is irrelevant. This gradient doesn't give you, let's say, a good improvement in your model, right? So those SIs need to be weeded out, right? Those small samples needed to be weeded out from your data set, right? So you don't have actually much direct control over your data, because at the end of the day, we all know that this process is very data hungry. So we use the data as whatever that we get, right? But yes, I mean, data cleaning is needed. Entropy is to be maintained, right? Entropy is to be sort of improved, and core set is one mechanism by doing that. Well, I mean, I could also say you something like maybe a bit aside. So for example, when we talk, right? So a lot of time when we say same thing, right, several times repeatedly, so it becomes boring. So idea is that take the boring data out, right, and keep more interesting, more diverse data. Okay. Then how do we measure, how do we ensure ethical considerations and integrated over training generative models to biased or harmful outputs? Very good question. And, maybe I will just talk about federated learning. So that is one sort of approach where data that is collected, right? We ensure that, okay, there is some.
Sorry.
It's okay. It's okay. But yes, yeah. But let's yeah, let's keep this discussion more engaging and interesting. Okay, good. So to avoid the data is biased, right? So federated learning is a process where where we train the model, right, on the data sources itself, right? And in that kind of a setting, when we update the model, well, I mean, I will talk about federated learning just in a bit. We update the model, we actually see that, okay, the gradients that we are getting, the updates that we are getting, if that is sort of troubling our model, creating some kind of bias, and so forth, right? So idea is that, I mean, the bottom line that I can tell you is that at the end of the day, when we are doing the training, all that is happening is that at every step, the gradient update is sort of changing your model. So to mitigate bias, to mitigate anything harmful, people have been exploring, and a lot more has to be done. That just check at this step, the moment this update is happening, if you could check the harmful things, I think the finally trained model will not be the problematic one. Also, people, I mean, maybe some of you have already sort of stumbled on this kind of interesting info that this DeepSeek R1, when it was released, I believe it was on January 22nd or something, maybe January 16th. I don't exactly remember the date. But then, people started asking it that how many states are there in India? Okay. And then it said, okay, 29 or maybe 29, right? And then they asked DeepSeek, okay, list out those states, and then it started listing out from Arunachal Pradesh. And by the Chinese government policy, Arunachal Pradesh, they have a dispute over. Okay, and then soon enough they realized that okay, the Indians are playing with DeepSeek. So then at the inference time, so they sort of created, Arunachal was missed exactly. And then at the inference time, they created this check that, okay, Arunachal Pradesh was not shown, or later, they also sort of started giving this information, no, this is beyond my capacity, things like that, right? So this is called, this is called information time debiasing, okay? So when a new model is released, right, or maybe when, let's say, so think about this scenario that you purchase such a trained model, right, from a company, and then you want to sort of use it for whatever purpose, right? So you can test that model several times, right, with different kind of benchmarks and so forth. And then as soon as you figure out that okay, this is not a robust model, or this does not or this is a biased one, so you can do some kind of inference time debiasing. So that is another sort of approach for sort of checking the harmful things. Okay, good. All these great questions, but that question, but these questions are of course set up for the tempo. But I need to go to more basics. Any question with the setup that I just left you with? So we have the model, a d-dimensional vector. I'm just reiterating myself, and then we have the gradient updates. Okay, cool. So with that, let me move forward. Okay. So, okay, so we said that, okay, we have training data and then we have model, right? Now, now let's come to the scenario when the training data becomes big, right? So as soon as the training data becomes big, when we say big, it is like, trillions of tokens. And in fact, we just saw that this Cosmos database has actually some thousands of trillions, which is actually, gazillions of tokens, literally, right? So then a big training data, then your training process starts feeling hit, right? And then as soon as not only the data is big, but also your model is big, uh, the training process is really under a lot of hit, right? So how to deal with this scenario when you have big data plus big model? Okay, so one sort of one side, let's say, or branching of this, data collection process is federated learning. So, or decentralized data. So what we do is that suppose we have some n data sources, right? So they have their own little data, S1 to big S1 to big Sn, right? And then they don't want to share data. So so maybe I can also mention here that recently there was a lawsuit filed against OpenAI in India, and I think there was some info that Sam Altman is again supposed to visit India. Maybe he has meeting with the Prime Minister and so forth, right? So some Indian news channels have actually filed a lawsuit against OpenAI that they have collected the data, published on data in the sense that just web articles, right, published on the Indian news sites, and they have trained their model on this data without actually giving them ownership of the data, or without perhaps even sort of so essentially, let's say when you write something, a poem or a book, or maybe someone writes a news article, right? It's their property, it's their proprietary things, and they should be credited for that, either monetarily or otherwise. But data collection has become a big issue, and all these big model training sort of setups are collecting data without informing people, and it is actually data stealing, right? So how to deal with such a scene, such a problem? So idea is to make the to make the model training decentralized. So one such application is your Google Keyboard, right? Google Keyboard app. So I believe that many of you have actually Google Keyboard installed on your mobile. Maybe you have some other keyboards, but the keyboard app on your mobile is a very good example of federated learning. So what happens is that when you type something, right? Let's say if you type a sentence, this is actually your private data, right? So this data, even though your mobile is connected with, let's say, the server, Google server, but Google by law is not supposed to collect this data, right? So what do they do then? And they also have to sort of improve their keyboard app so that it could do good query prediction. Okay. So what they essentially do is that when you install the Google Keyboard app, or for that matter, some other keyboard app, right? These days, although maybe many of these keyboard apps are already pre-trained and very well working, but suppose they have to improve it. So they will install a small model, right? A small neural network on your mobile. And then when your mobile is idle, right? This small model will train over, the sentences that you would have typed. So the sentences that you typed, the app actually stores that on your mobile itself. It does not, by law, of course, it does not have to sort of transmit that sentence to the Google server. Okay. Once this training has happened, right, locally, then then the keyboard app will actually synchronize with Google's data center, and thereby this synchronization is essentially just passing the model state, not the data itself, not the exact sentence that you would have typed, but just the model's state, and then the synchronization happens at the big server, and thereby this keyboard app is improved, so well. So this particular scheme, this federated learning approach, is also very much applicable for the large language or generative models, where if they cannot collect the data lawfully, right, then they should rather, but they don't do it, but they should rather train the model locally, and then can synchronize it across. And some people actually predict that this approach, the federated learning approach, is going to be perhaps the de facto approach when these models, the AGI and so forth, right, artificial general intelligence, as it is said, when that has to happen, then it has to take the intelligence, right, of everyone on the planet. And how to do that? Of course, you have to do some kind of decentralized training. You just cannot collect everyone's private data. Okay. So I hope this setup is also kind of gives you some idea of what we are sort of facing. Okay, so having done that, now I'm going to sort of talk about this distributed machine learning. So what I would I mean, why I'm bringing distributed here. So we all understand, right, that as soon as we have a big computational problem, then of course multiple machines are to be applied, right? So one computer is not good enough, one GPU is not good enough, so multiple GPUs and multiple multi GPU computers are to be connected together to train the models, right? And that is called distributed machine learning or distributed training. Okay. So my plan for this evening is that I will be talking about a systems perspective, right, for the distributed machine learning. And after that, I will also give you some theoretical perspective. Those who are interested in teaching the theory, or at least some formal discussion, of machine learning training in your courses. I hope that this will be of some use. Okay. All right. So I don't know if I should again pause for a minute and then ask if there is any other question. Yeah. Okay, cool. So I don't see anything coming on the chat window. No hands raised. So then I move. Okay, so systems perspective. So because we are talking about distributed machine learning, so there are two, computer science concepts here. One is of course distributed, and the other is machine learning. First, let's talk about distributed, right? So essentially, we are talking about distributed systems. Okay, so the distributed systems, right, are categorized into two categories, right? One is the shared memory distributed system. The other one is message passing based distributed system. What is shared memory distributed system? All of you actually, uh, uh, have shared memory distributed system. What about data privacy with DeepSeek? We know perhaps as little as anyone else, right, on the planet at this point. So we don't know how DeepSeek collected the data and what exactly they did. I mean, OpenAI is claiming that they distilled their model. Essentially, what they are saying is that they used the OpenAI's model to create their data. So data privacy and so forth. We don't know. So when if they can play with such a big player, then why not? I mean, if you are doing some chat with this DeepSeek chat, right? They can collect your data. But I hope that they don't. I mean, there are now some other alternatives. So some players, including I believe that in India, this Ola, right? No, wait. Yeah, Ola, right? They are the ones who have this project called Kritrim AI. Anyhow, so what they have done is that on their cloud now DeepSeek a pre-trained model has been deployed. Right. Similarly, there are so many. Even Microsoft on Azure has deployed the DeepSeek pre-trained model, and you can rather maybe do some inference chat with. I'm not sure if they already have a chat version or a chat leaderboard. But if you don't want to directly sort of communicate with the Chinese DeepSeek company, you can actually communicate with maybe Kritrim AI, right? But data privacy, yes. I mean, DeepSeek may collect your data if you chat. Okay. All right. Any other question related to the setup that I left? Okay, cool. All right. So then distributed systems, right? So like I said, that distributed systems come in two flavors: shared memory and message passing. All of you actually have shared memory distributed system. And do you realize that you have actually access to a shared memory system on your hand, even at this point? Yes, so all of our mobile devices, right? Our laptops, all of them have multi-core uh, processors, right? So your mobile devices most often have Snapdragon processors. Your computers are at least like quad core. Maybe some of you have dual core, some of you have octa core. But what does exactly that imply? That you have actually multiple cores, and that access that those cores actually access the shared memory RAM, right? So this is actually shared memory distributed system. The processing will happen on different cores here. You can see that cores have their some individual memory, but this shared memory, which is RAM of your either mobile device or your laptop, creates one distributed shared memory system. Okay. The shared memory system can sort of again be categorized into two flavors: synchronous and asynchronous. Synchronous is when the cores, as they do the processing, they have to work in lockstep. So once so let's say one task is assigned, then all of them will first finish that task, and only after that they have to go to the next task. So that is synchronous idea. The other one is asynchronous, where uh, read-only memory is shared memory. Usually the shared memory system that we know or that we sort of refer to here has to have a write option, right? So read-only memory is not shared memory. If you meant to say RAM, right, random access memory, then exactly RAM is shared memory, right? But not ROM. ROM was I don't know. So these days we actually don't have any ROM. So ROM used to be maybe some 15, 20 years ago when we used to use those this thing, right? Non-writable CDs, right? So those were actually ROMs, read-only memories, right? Even the CDs, DVDs later became perhaps writable. Anyhow, so RAM is shared memory, shared in the sense that it is actually shared by the multiple cores of your mobile or laptop device. But here, beyond that, we are talking about shared memory distributed system. So not only the memory, but our system, the distributed system from computer systems perspective, it actually includes this entire setup, right? It includes the core, and then it's the core's cache memories, and then the RAM, right? Which this cache memories connect to. Okay, so we are talking about the system, not just the memory. So this is shared memory distributed system. Similarly, you have message passing based distributed system, right? So essentially, you have like multiple, multiple machines. Each of them have some processing and memory, right, connected with each other through a communication network, and then they sort of communicate with each other via message passing. Again, it can be categorized into synchronous and asynchronous, right? Synchronous when when all of them have to move together. Asynchronous when that can be sort of relaxed. Okay. All right. Any question about distributed systems? Okay, cool. So distributed data, like I said, that it could be centralized, decentralized. So centralized is more like what OpenAI or Gemini is doing, right? So they have collected the data by doing web crawling and other means, right? And say in their server, and thereby they are doing the training over a centralized setup, right? The decentralized is the one that I talked about. In a federated setup where you have the data sort of stored over different sources. Okay. Now, again, just a little bit mathematics. Please feel free to stop me if you sort of have any issue with any of these notations. Okay, let me explain what these are. So now recall, I mean, I just talked about this BI. This is our mini batch, right? Mini batch. Okay. Then XT, this is our model, right? Or maybe neural network, or maybe our transformer model, whatever that we are talking about. So let's call it just a model, right? So model after the iteration T, we are doing iterative training. So this is iteration T, right? So after Tth iteration, we have the state of the model represented as XT, okay? And then at that state of the model, we are doing one mini batch sampling, right? And this I is the index of the processor, right? Processor or the machine. So suppose we have altogether n machines. So there are n machines. Let me call it machine or processor, right? Well, I mean, I'm writing on my screen and it's not very efficient, but I hope you can still read what I am writing. So we have n machines, and then and then each of them are computing the stochastic gradient, as you can see. So machine I will compute the stochastic gradient as nabla f xt bi, right? And thereafter, what will happen is that we will have to sum up all these stochastic gradients over computed over the different machines, and then compute the average. As we divide that by n, it gives us average. Multiply that with our learning rate, right? Learning rate, and and thereby we obtain this update. So this entire thing is one update, right? One update. And once we have the update, then we update our model from xt to xt plus 1. Does it make sense? The update step. So mathematically, this is exactly what is happening in a distributed machine learning training system. So you have multiple machines computing the gradient. The gradient is being summed and averaged, and thereby the model is being updated. Okay, what are the issues that this particular process can face? Of course, with synchronization, synchronization is a huge requirement. So I'm not sure how many of you noticed that when I sort of talked about this shared memory distributed system, or for that matter, your message passing based distributed system, the synchronous systems requirement is that all of them first compute it, and then only they can take the next step. It is entirely possible. It is entirely possible that different cores have different speed on your laptop, right? For example, or for that matter, if you have a message passing based distributed system, then different machines have sort of different speeds, right? And if they have different speeds, we cannot perhaps expect all of them to be working in a lockstep, right? We cannot expect them to be efficiently working in a synchronous manner, right? So therefore, what will happen is that the synchronous training will have a lot of overhead, right? A lot of time latency overhead. So that's a big issue with synchronization requirement. Okay. The second issue that we are going to face, and that I'm going to actually make you realize here, is the gradient size. Okay. So what do we mean by that? So notice it here. So if your x belongs to something like, let me write it, a bit more practically. So let me do it this way. Okay. So now all of us understand, all of us have heard that that our or we actually saw, right? Why heard? We just saw that these models have a trillion size parameter. So suppose our x. Any question? All right. So suppose our model x is actually a vector in 1 trillion dimensional, right? So this is like 1 trillion dimensional real space. Okay. So 1 trillion dimension. So mathematics says that if our model is 1 trillion, model is a vector of 1 trillion, indices, right? 1 trillion dimension, then our function, this function's gradient, the nabla f, will also, this is also a vector, right, of dimension 1 trillion. So this nabla f also will belong to R 1 trillion. Okay. So now let's try to understand, what are the implications of that. So if we are, trying to train a model of dimension 1 trillion. Okay. So what is the sort of size of one so essentially we are saying that one gradient update will include actually communicating. Let's say when we are using our message passing interface, so we are saying that one gradient update will require communicating 1 trillion size vector from this machine to all other machines. Okay, all other machines. So 1 trillion size, right? So one float or one double, right? So it's a vector where each of them are one double, right? One double. Okay. So all of us understand this programming introduction, right? So one double. So this is essentially what? This is 8. Well, I mean 64 bit, right? Or 64 bit or 8 bytes. So let's use 8 byte. So this is 8 bytes. So one double is 8 byte. So essentially, what we are saying is that we want to exchange 1 trillion of such, double values, right? So what will be the size of one gradient? So if I could do some very quick computation, it is like 1 trillion into 8 bytes. So essentially 8 terabyte. I hope you are getting now a sense of the problem. So if you want to train a model of size 1 trillion, right, you will have to communicate 8 terabyte, across this network, which is just not possible, right? So, from our knowledge of developments in computer networks, we know that all these high-end InfiniBand switches these days, I mean, some of them are 100 gigabyte per second, right? Maybe there are still some higher end, maybe 1,000 gigabyte per second and so forth. But yes, so it's like beyond that, right? So it is something like 8 terabyte. So even if we use maybe a switch of 1,000 gigabyte per second, right, it will require you to do at least 8 communication. Right. So, and in any case, I mean, for 100 gigabyte switches, which are like more common, you will have to do something like 80 communication rounds to communicate one gradient, right? That's a very inefficient way. So we actually face a big issue with this limited bandwidth. And for that, there are different techniques such as gradient sparsification, compression, and combination of sparsification and compression. So maybe in a bit I will be just talking about them. But again, to give a very rough idea what we mean by the by the sparsification. So suppose I have a vector of size 1 trillion, right? What I would do is that I will maybe using some sampling, I will pick I don't know, maybe 1 million of values from here. Just randomly pick 1 million of these values and communicate that. Instead of sending a vector of size 1 trillion, just pick 1 million and send that. Okay. So what will happen? It will actually lose a lot and a lot of information, right? But at the end, at least what will happen, that we will have model training happening, right? So model training will not be affected by doing this specification. So this is one approach of doing sort of addressing the limited resource constraint, right? Similarly, the gradient compression. So in compression, what we do is that instead of sending 64 bits, right, so we will just send, I don't know, 2 bits or maybe 4 bits for every double, right? So it is like it is called compression, and thereby you will have something like a lot of saving on your communication across the network. You can also combine that. So this is combination of the sparsification compression. So these are like practical system related tricks that we apply to train these models in a distributed setup. Any question? Okay. So look, I mean, we can talk about all these, let's say inference time things, right? How DeepSeek is doing and so forth. But what I thought is that I actually leave you with some more fundamental, ideas about what exactly is happening under the hood, right? I hope it helps. Okay, cool. So then let me again show you. Sort of a bit more about what we could do more than just sparsification and or compression. So this is called local SGD. What we mean by local SGD? So idea is that suppose if you have like multiple data centers, right? So suppose Google itself has multiple supercomputers in a data center, right? So instead of transmitting the data across all the machines all the time, right? All the machines all the time, what you could do is that you actually train the model locally, right? You train the model locally. Therefore, we are calling it local SGD, right? On each of these machines. So all of them are like big supercomputers with multiple machines there, right? So you train them locally, and after maybe some k steps, after something like 20 steps, you communicate it across. Okay. So therefore you directly save a lot of communication. Okay. So it is another sort of approach of dealing with the limited bandwidth setup. So here is a formal sort of description of this local SGD, right? Local because we are training it locally for many steps. It is very similar to federated learning, but without going into federated learning at this point, I'm just talking about the distributed training. So in local SGD, you train it for k steps. So let me again sort of give you what is exactly happening. So X is our model as earlier, right? X is the model. Okay. J, this little j is the index of how many rounds you have, communicated across, right? So we communicate after maybe doing some 20 local training, we will be communicating across the machine. So this j is an index for that. This little t is the index for the local number of training steps, right? So therefore, here we have so we are saying that okay, t goes from 0 to k minus 1. This particular notation is actually 0 to k minus 1. Okay, so we have done some k training. 0 to k minus 1 means k training steps locally, right? And after that, so at every step we have locally updated the model, right? So here this one is local update. And after that, what we do is that for the kth round of synchronization, we just take those models, right, from the local machines, communicate it across, and then we do the averaging. Once we have done the averaging, thereafter we have obtained the next state of the model. Okay, so that is called local SGD. Does it make sense? So what I'm trying to say, I mean, without sort of, if you had any issue with the notations, don't worry. I mean, it is very simple. Idea is that train several steps locally and then do the averaging. Okay. All right. So that is local SGD. Again, this one will face issue with synchronization when you have to sort of wait for of course synchronization is happening, right? So this is at the end you are doing the averaging. Averaging means synchronization here, right? So when you are doing this averaging, you actually need input in terms of the model state from all the machines. I is index of machine, right? There are n such machines, let's say. So you need input from all the machines. And again, if some machine is slower, all of them will have to wait, and thereby there will be issue with synchronization. And again, limited bandwidth, because you still have to do some communication. At least it's not something like totally communication free. There is some communication. Okay. So this is another sort of training process. What I would do is that I will skip this part in the interest of time, asynchronous training, but but you can maybe check out about that. Federated SGD also I will skip because we are left with some limited time. So let me then, having given that, let me then take you to sort of even more lower sort of, in local SGD, how data sets are assigned to different machines for training. Very good question. So idea is that your these servers, right, or let's say these computers, the supercomputers, usually they have something called NAS, network assisted storage. I believe that many of you would have heard about it, right? So network assisted storage is something which is connected with every machine, right, together. Notice that the processors are sort of now partitioned, right? Or let's say processors are distributed. So different, let's say, computers have their processors, doing processing locally, but all of them are connected with the same. Same network assisted storage or same data storage. If that happens, then all of them have access to the same data. Okay, but still, we have to do the training. We have to do the training in such a way that that entropy is maximized. We just said, right, that all of them should not be doing the same update, right? So that it is sort of irrelevant. So what we usually do is that, suppose our data, right, our data sample S is something like I don't know, S1, little S1 to something like SL. Suppose we have L samples. So we know that, okay, index, these samples are indexed by 1 to L, 1, 2 to L. So what we will do is that we will, at every synchronization round, we will just partition this the index space. Okay, so randomly we first shuffle, right, and then partition this. Once we partition this, then we know that, okay, these machines have non-overlapping indices, right, and thereby locally they will be training for some k steps for the chunk of data that will correspond to these indices, right? And thereafter they do the synchronization. In the next round, they again sort of get different indices, and thereby they do it. Okay, so this is about local SGD. I mean, you may then ask that, okay, what about federated SGD? Well, I mean, federated SGD doesn't even have to sort of consider, face this issue about data partitioning, because anyway their data is sort of private, right? They don't share data among themselves. So so whatever data that comes, you anyway have to deal with that. But in local SGD, the partitioning of data happens, or assignment of data. The question was how data sets are assigned to different machines. The assignment happens by partitioning the indices into chunks. I hope that answered. Okay, cool. So yeah, so then going a bit further down, right? So we just said that models are now huge, trillion size models. And then I don't know, maybe if some of you have kept track with the developments in data loss is there in local SGD. We should not say data loss, right? But loss is more in the sense of loss in the gradient. right? So as you sort of communicate, let's say some sparsified gradient and so forth, maybe you have some information loss, but not data loss. Data, you actually use entire data. But yes, after you have computed the gradient, have processed the gradient. Yes, I mean there you face some constants like network bandwidth or maybe some other issues. So there is some loss in the information, but not data exactly. Okay, cool. So then we said that the models are big, trillion size and everything, right? And then we know that, okay, our GPUs have limited memory. So it's only natural that these models cannot fit on single GPU, right? So therefore, what we need to do is sort of have the models on multiple GPUs, right? So multiple GPUs. So this is also called model parallelism. Okay. So what is model parallelism? Idea is that uh, you actually compute the forward pass. So I believe that you understand, right? The forward pass and backward pass, right? So forward pass is when you actually compute the neural network, right? And thereby the computational graph is created. After that, as you do the back propagation or backward pass, you compute the gradient. Okay. So so idea is that you have multiple GPUs, and then or for that matter multiple machines with multiple GPUs, and then you will compute it chunk wise. So the model is essentially said to be, so let's say this one will sort of hold maybe x1 2. So if our x belongs to rd, right, a d-dimensional vector, so this one will hold from 1 to, I don't know, I1, right, I1, and then this one will hold x I1 plus 1, I1 plus 1 to I2, and so on and so forth. And finally, this one will hold something like in plus 1 to d, right? So this is like partitioning the model. So model has been now distributed over different GPUs. Okay. So then as you do the forward pass, right, as you do the forward pass, you first let's say this is our the pipeline, right? So first maybe this GPU does the computation. Once it has done the computation, it will pass to the second one, and so forth. Uh, uh, so notice here the parallelism, this pipeline parallelism. What it does is that initially maybe all but one GPU or all but one processor will remain idle, right? But as soon as all of them start getting their task, then it creates actually a parallelism, a pipeline, right? So then all of them are engaged, and at the same time they will be also doing some computation, right? So first the forward pass is done, and then once the forward pass is done fully, then your model is computed, the computational graph has been computed, and then you would do again the backward pass in the same way, in a pipeline manner, right? So those who have sort of seen different approaches of parallel programming, pipeline parallelism, I believe that pipeline parallelism we also teach in operating systems course. Anyhow, so idea is that pipeline parallelism is one approach by which different multiple GPUs or multiple machines can be engaged to train the very large size models. Okay. Now, okay, before this pipeline parallelism, everything that I talked about was data parallelism, right? So here, we said that okay, multiple machines will have different. So here, this was about the data, right? So data was sort of partitioned across different machines. Here we said that okay, we can do pipeline parallelism. So it is natural to sort of guess that we will soon enough face the scenario where not only the data is parallel, but also model is parallel, and therefore we need to do a combination. So this is data model parallelism. So essentially what you do is that you do model parallel on multiple workers or nodes, right? So on every worker you have, so for example, data parallel rank 0. So this is, let's say, one supercomputer where you have, let's say, 4 computers, and then in each computer you have again multiple GPUs, right? And thereby you are doing model parallel trading locally, and then you are computing, then you are sort of communicating and then so both these supercomputers have their own local model parallel training, and then they are communicating across, right? And as they are communicating across, this is then data parallel training. So they have their own chunk of data, and then model parallel happening locally. So this is data model parallelism. Even further down, right? Not only data model parallelism is good enough, but there is also uh, uh, even lower than that. So that is called tensor parallelism. So you can also face even bigger models, right? So no, model parallelism plus data parallelism is not sufficient. So therefore, what we do is tensor parallelism. So so idea is that every layer, right? Every layer of a neural network. So let me represent a neural network very quickly, like this one, right? So every layer of a neural network has different nodes, right? And these nodes have weights and biases, right? Weights and biases, WP. Okay. And these weights and biases are at the end tensors, right? So tensors are essentially multidimensional matrices. You have multidimensional matrices. So those matrices represent those tensors, right? So these tensors themselves becomes so huge, right? That so think about the scenario when you are dealing with something like 100 billion size of a model, or maybe several trillion, 10 trillion size of a model. Then each of these layers and each of these tensors themselves becomes too big, and thereby these tensors need to be processed in parallel, and therefore we call it tensor parallelism. So essentially what you do is that a tensor have sort of multiple layers of matrices, right? Multiple layers of matrices. What you do is that every layer you create chunks, right? And then you assign one chunk to one GPU. You see, so thereby the parallelism actually has to go so to so low level, right, such that the processing could be enabled, right? Well, I mean, I believe that all of us understand that at the end of the day, right, at the end of the day, all of this thing, machine learning, entire machine learning is what? It is just matrix multiplication, believe me. I mean, if we understand matrix multiplication or matrix operations, let me better write it, matrix operations, or this very basic linear algebra properly, right? This is just building on that and building on that. This entire mathematics and the engineering is about doing more efficient matrix operations, right? So you would have realized, that we started with talking about DeepSeek, and then we talked about multiple machines, and now we are at this stage where we have this matrix operation is being parallelized in the sense that we have different chunks being assigned to different people. So this is called tensor parallelism. Tensor is multidimensional matrix, right? So this is multidimensional matrix. Multidimensional matrix. So what will happen is that as we do the matrix operations, you do the same matrix operation on different layers, and that is tensor operation. So essentially, these tensor operations are then parallelized using multiple GPUs, right? And you do the GPU wise computation. After that, you collect that, and then you have so first GPU wise computation, then the sister, a machine wise computation, and then that is collected to one cluster, and then multiple clusters sort of communicate with each other. Okay, so that is sort of more or less high level, system oriented view of distributed machine learning or distributed training. Any question up until here? So I'm left with roughly 10 minutes. I don't know. Okay, so if everything was fine, then very quickly, I don't know, maybe I can also talk very little bit about the theory of this engineering, right? Because theory is what sort of is at the core. Okay. All right. So theoretical perspective, I talked about system perspective, now theoretical perspective. So idea is that for distributed machine learning, you take the sequential machine learning theory, and then, you have to extend your theory so that you could tame the distributed systems specificities. In particular, for example, if you have multiple machine, and then there is communication, some communication loss and things like that, then how to do? The question is that how does tensor parallelism help with memory limitations of GPUs? Good question, actually. So tensor parallelism is, because we have memory limitations of GPUs, right? You see, I mean, okay, so I could give something like this info. So in 2008, when it was like very first version of CUDA enabled GPUs, at that time, so this was like when I was doing masters, right? So at that time, GPUs used to have something like just 1 GB memory. One CUDA GPU and NVIDIA GPUs had just 1 GB memory. These days, I mean, we have 200 GB memories on GPUs, right? That's why this H200 and G200. Anyhow, so those 1 GB GPU memories, right? We had to do like back and forth. So first you do the first you do the computation on one data chunk, and then you transfer it back to the CPU, keep it on your keep it on your RAM, right? The result of the first sort of computation step, then do the second computation step, then the third computation step. So you can see that this was unless your problem is embarrassingly parallel. What is embarrassingly parallel? One that can be parallelized very efficiently. And unless your problem is embarrassingly parallel, this kind of trick was not very successful, right? So anyhow, so now coming back to here, so tensor parallelism with the memory limitations of GPUs, this is like one idea. So this is also called external memory computation. Although now with this high-end GPUs, right, 200 GB, 200 GB kind of memory on the GPU. Essentially, what we do is that we just assign that chunk of data which could fit on one GPU, and thereby we could sort of do more efficient computation. We don't have to do this external memory and so forth. A specific distributed machine learning applications, if I read it correctly, DML, if that stands for distributed machine learning, right? Then I would say that you know everything that we are discussing here is actually distributed machine learning application, right? So distributed machine learning is the sort of back-end idea of your generative model training, right? So application of distributed machine learning will be anything large scale training. Okay. Look, so machine learning. So this is this particular question can actually have two connotations. When we say machine learning applications, right? So then we understand, okay, machine learning for good, machine learning for, I don't know, some cancer detection, maybe machine learning for so many different things, right? Machine learning for even space, things like that. Okay, but in particular, if you talk about distributed machine learning application, I would say that it is training large scale model. Okay, once your model is trained, then you can sort of use it for everything, right? So thanks for your appreciation. So what I would say is that all that matters is that how efficiently you can train the models, right? How big data you have used, how many tokens you have used, right? And then you know then only you can think about sort of doing all sorts of inference time tasks, right? So all these multi-model and so forth, different foundation models, right? You need to do distributed machine learning in the backend. Okay, good. I don't know. So if I would anyway have any time at all to do anything in terms of theory, yeah, I will have to. Maybe I can actually show you some in 5 minutes some cool figure. Okay, in the theory, what exactly happens, and then I will stop. Okay, so let me show you. So what exactly happens? You see, so this is a representative figure, right, of our neural network. So like we said, that neural network at the end is just a function, right? This is a function. Here I have just, for obvious reason, I have just not considered S. But our neural network is function of model, right? Which is, this X belongs to D-dimensional real space, and then our data, which is again, huge size. So essentially, size of our data is these days maybe trillions, right? So several trillions. So maybe 10 trillion, something like that. Okay, so size of this data. So this function is it is actually a very high dimensional function, and then in a visualization setup, you can think about this function being something like this, right? And then the idea is that as we start our sort of training process, the function or the model is untrained, right? When the model is untrained, essentially what it means is that the error is quite high. So here you can see a visualization in a two-dimensional setup. I'm sorry. Okay, so there is some disturbance, but anyhow, let me continue because I am left with only 5 minutes. So you can see that here, so your function which is representative of your empirical error, right? So it is quite high. Okay, it is quite high here. And then as you train your model, iteration after iteration after iteration, you actually aim to reach this state, right, where where the model's error will be minimized. Essentially, this function will take the minimum the most optimal minimum value, right? So minimum possible value. And so theory of this machine learning training is all about tracking the dynamics of this vector minus gradient fx or minus nabla fx. So as it moves from here to there, right, you have to track it, and then you have to sort of figure out that, okay, what are the problems that it may face, and then whatever problem that it faces, you have to sort of characterize that mathematically, and then you say that, okay, let's say if I come up today, tomorrow with some new training process, then that training process, if it does not trace this path, it may trace maybe some path, right? Maybe some path, it may go there, but at the end, eventually it has to come to this point, right? Then only our model will be trained. So this is the mathematics. So maybe some of you would have heard about these recent developments in this domain, something called low rank adaptation, or LoRa, right? So low rank adaptation, right? LoRa. So this is now a very common, approach for fine tuning the large language model. So these days, all the kids, right? They are just downloading some pre-trained models from Hugging Face, right? Hugging Face is the site to download pre-training models, right? And then they are applying LoRa on maybe one GPU or say a couple of GPUs. So LoRa actually, so this is perhaps the best path that your training would have taken mathematically or geometrically, right? LoRa would take you maybe, I don't know, somewhere here and there, right? But at the end, it will hopefully take you to a bit more optimal state of your model. And similarly, there are other such processes called zero offload and so forth, right? I'm just noting them here, but all of them are sort of the engineering outcome, right, of training the large models on limited resources. However, being in academia, and in particular, if you are interested in exploring research in this domain, you have to also get a bit into the theory and get an idea of what is happening, the dynamics of the optimization process. I don't know if I should go any further in the theory, but yeah. So let me leave you with that, because yeah, it's time. So then I invite your further questions. I hope that it has given you an overview of distributed machine learning and training large scale models.
So if you have any question, just we can take one or two questions.
Can we combine tensor parallelism with other parallelism strategies? Yes, yes, of course. Yes, in fact, that's what we, I mean, all these training processes do. And how does it affect? One line answer that I just said, that your training dynamics actually takes different paths. What will happen is that sort of maybe it will not reach all the time here, but it will reach somewhere here, which is kind of good enough for you. Maybe I could also tell you a bit more about the mathematics part here. So if you still remember, right, the rank. So rank of a matrix, right, at such a high dimension, which is something like 1 trillion cross 1 trillion, right? So we know that what is rank? So number of linearly independent columns in a matrix. So it is already like a very active area of research, that the rank of these high dimensional matrices or tensors, that is quite low, right? Intrinsically those are low. So a lot of vectors are there which are linearly dependent, or linear combination of different columns here. So therefore this low rank adaptation actually performs quite well. So by doing the tensor parallelism and data parallelism and everything together, right, well, I mean, we feel that maybe there will be some effect, but actually we don't know that how much is the issue, right? Mathematically, how much it actually affects, because at the end of the day, we don't understand that what kind of function itself it becomes, right? So you can see that this function shape is still sort of very funny, right? So it is still just 2 dimensions. So try to visualize. I mean, human mind, we cannot visualize anything beyond 2-3 dimension, right? So here 2 dimension, why I'm calling it 2 dimension, because function is of 2 dimension, and the third dimension is for the function's value. And imagine that when we are dealing with something like a trillion dimensional space, so we really don't know what exactly is happening. Yes, some effect happens, but we never know. Maybe it doesn't affect anything if we are doing tensor parallelism, data parallelism combined. Okay, I hope that answered your query. Any other question?
Any other quick question? If there is any question, please raise your hand or type in chat box. So I don't think there is no more questions. So please, there.
Yes, sir, sure, sir. Thank you very much, Dr. Bapi Chaterji, for your fantastic session on training generative models. The depth of knowledge you shared on model training techniques and optimization strategies was truly valuable. Your session has provided us with a strong foundation to further explore and apply these concepts in real-world AI systems. We appreciate your time and effort in making this session so informative. Thank you once again.
Thank
Okay,
you
thank you,
for
Bapi
having me.
Chatterjee, for accepting our request and for your nice session.
Thank you, Professor Anurag, and thanks everyone for your time and attention. And I hope that it helped. So hope to see you somewhere, sometime in person, right? So with
Okay,
that,
thank you. Okay,
yeah.
sure.
Okay, thank you then. Bye.
Bye, thank you. So Agrawal sir, have you joined?
Hello.
Yes, sir. Good
I have
evening, sir.
joined.
Good evening, sir. Sir, we can test your just voice. If you can speak, then we can confirm if
Yes.
it's
Am I audible?
Yeah, perfectly. Sir, good evening, sir.
Good evening.
So, Pradeep, please initiate.
Yes, sir. Next, we are thrilled to welcome our second keynote speaker for the day, Dr. Ramesh Kumar Agarwal. He will be discussing Vision Transformer Model and its applications. Dr. Ramesh Kumar Agarwal is a professor at the School of Computer and System Sciences at Jawaharlal Nehru University, JNU, New Delhi. He holds an MTech from the Indian Institute of Technology, Delhi, and a PhD from the University of Delhi. With over 30 years of teaching experience, Dr. Agarwal has held several key administrative positions at GNU, including Chief Coordinator of Communication and Information Services since August 2022, Dean of the School of Engineering from January 2018 to January 2020, and Dean of the School of Computer and System Sciences from July 2015 to July 2017. His research interests encompass data mining, machine learning, pattern recognition, medical imaging, and information security. Dr. Agrawal has an H index of 17 with over 1010 citations to his work. He has authored more than 55 journal articles, 3 book chapters, and 48 conference proceedings. Dr. Agarwal's notable publications include fast and robust spatial fuzzy bounded K-plane clustering methods for human brain MRI image segmentation, published in Applied Soft Computing 2023. Enhanced depression detection from speech using quantum veil optimization algorithm for feature selection, published in Computers in Biology and Medicine 2022. Bias corrected intuitive fuzzy C-means with spatial neighborhood or information approach for human brain MRI image segmentation, published in IEEE transaction
I
on
think
fuzzy systems.
let's fully stop this. Okay. So we
Okay,
can
sir.
You can
start now.
shorten
Okay.
and welcome, sir. You can shorten and
Yes, sir.
welcome, sir.
Welcome.
Ah, okay. So I think I am audible. And is this slide visible
Yes,
to
sir,
all of you?
perfectly. Yes, sir.
Is this slide visible?
Yes, sir. Yes, sir. Visible.
And is it moving also?
Yes, moving, sir.
Okay, thank you. Thank you. So I think I thanks Dr. Anurag for giving me an opportunity to speak on this topic, Vision Transformer. I think this is the uh, model, I think, which is quite commonly used these days. Okay, so I would like to tell you the basics of Vision Transformer. Okay, and if you have any query, you can stop me in between and I have your queries resolved. Okay. So my outline of presentation will be, first, I'll discuss with few examples, applications of machine learning. Then I'll discuss again briefly a neural network. Again, briefly convolutional neural network. And then we will talk about how transformer is different from convolutional neural network. And how transformer, which was originally suggested for languages, NLP kind of work, how it can be extended for images and videos. Okay. And lastly, it will be followed by a conclusion. So I think this is well-known example, okay, where machine learning is quite successful in recognizing faces. So you know that biometric system based on faces, biometric system based on finger, biometric system based on iris. Okay, so there are various kind of biometric systems are designed, and all these are examples of machine learning. Similarly, face uh, recognizing different face expression. Okay, it has associated with to gauge the mood of the person. Okay, so many kind of disease or depressions can be associated with the help of understanding emotions associated with a person. Okay, then many kind of disease are diagnosed based on your retinal vessel segmentation. Okay. So this is also an example of machine learning where objective is that if you capture retinal images, okay, that is through fundus images, and we want to know the, you can say this arteries associated or vessels associated in your retina, because this will tell you what kind of disease the person may have, depending upon the structure of these vessels, depending upon the thinness or thickness associated with the vessels. Okay. So when you talk about machine learning, so image segmentation is also one of the important component other than classification. So similarly, we can talk about brain tumor segmentation and many more. Okay. But now let's discuss about neural network. Okay. So first of all, let's say we talk about a single neuron model, how it works. So if you think about that, there is a neuron. Okay. Okay. So this is a neuron. and there are many inputs are reaching to this neuron. And let's say these are the inputs X1, and the strength of this input signal to this neuron is, let's say, W1. And similarly, strength of the another signal X2, which is reaching to this neuron, is W2. And let's say similarly, the strength of kth signal is associated with the weight WK. And W0 is a constant input that is reaching to the neuron. So the net input that is reaching to the neuron can be easily computed as W1 into X1 plus W2 into X2 plus WK into XK plus W0. So now when a neuron is going to fire, we assume, let's say, when the net amount of the input reaching to the neuron is more than equal to 0. Or you can model with some other kind of function. Okay, so here we talk about that there is a function, okay, which takes input Z and the output is given by Fz. And in general, we consider activation function to be nonlinear activation function. Okay. So then there is an extension of your single neural network, because single neural network can solve only limited restricted problems. Means they can solve when the decision boundary is linear decision boundary. But in general, for most of the data, the decision boundary may not be linear. It can be non-linear. So then your advanced version of this neuron structure can be given by multi-layer perceptron, where we assume that your first layer is your input layer neurons, last layer is your output layer neurons, and in between you can have many hidden layers. But at present, I'm assuming that there is only one hidden layer. So in that situation, every node of input layer is connected to every node of hidden layer. And then every node of hidden layer is connected to every node of the output layer. So the input for an input X1, X2, X3, XD, the net input that is reaching to this neuron can be easily computed depending upon, that is, X1 into this weight plus X2 into this weight plus X3 into this weight plus XD into this weight and plus some bias, as we have seen in the case of single perceptron. So let's say the net input that is reaching to this jth neuron is given by net j, and the output from this jth neuron is given by, say, yj. So at hidden layer, we'll be getting output y1, y2, y3, yj. And these outputs will go as an input to the neurons associated with output layer. So we can again see what is the net input that is reaching to this kth neuron of output layer. So you will find that this will be given by y1 into this weight plus y2 into this weight plus yj into this weight and plus bias associated with this. So let's say it is given by net k. So for a given input net k, this neuron will give output, and let's say this is given by zk, which is f of net k. So I'm saying that when your input is x1, x2, x3, xd, let's say you observe output that is z1, z2, z3, zk. But for your data, you want that the target output which is given to you is t1, t2, t3, tk. And if this target output is different from your output observed by given by this machine, predicted by this machine, then we can compute what is the error. So let's say error associated with this model can be computed for a given sample. Just now I was present at the last moment, and then Dr. Bapi was talking about gradient descent method. So it is a very powerful method. So what it talks about, that I don't know what should be the weight of this network. So you are saying you want to learn a relationship between input and this target. You start with the random weights. Compute what is the output of this machine. Find out what is the error for this sample. So if you have an error, you change the weights. And so how you change the weights? You can use gradient descent method or its variants. So let's say for simplicity, what is your delta? By how much amount WKJ should be changed? So I say delta WKJ. So this will be computed by what? Minus eta del J by del WKJ. So let's say this is your, after solving, we'll get this. So we can easily find out that by how much amount I should change the weight of WKJ. Because I know eta is a learning rate. I can fix it. I know TK, I know ZK, I know at net K. So I can compute derivative of function of net K. I know YJ. So I can easily find out by what amount I should change the weights. Now, similarly, I can find out by how much amount I should change the WJI. So we are saying in this model, we were given training data. For a given training sample, I was knowing what is the target output. And for a given training sample, I got some output. And if this output is different from my target output, I will change the weights. So then again, I can take next sample. Again, I can find out what is the error. Based on error, I can change the weights. So I can keep on doing this till you find that model is giving error which is less than a particular threshold. Okay. So I think all of you know this, but I think the description of this was required because this will also be one of the component in understanding transformer. Okay. All right. So then let's see. We talked about that between input and hidden layer, output layer, I assume there is one hidden layer. So what is the role of many hidden layers? Okay. So what has been given by one particular research in by Hornick in 1991, that if you choose only one hidden layer, but if you choose sufficiently large number of nodes at the hidden layer, then we can learn the relationship between input and output. Okay. But take this example. So for this example, let's say I have given an image and the size of the image is 100 by 100. So the number of input for at this will be 10,000 features will be associated with this image. And let's say I'm solving recognizing English alphabet. So the number of classes are 26. So there are 26 number of nodes at the output layer. Now, as per Hornick, if I consider very large number of nodes at the hidden layer, say 10 to the power 6. So I can learn the relationship between input and output. But in the process, what is happening? The number of connections, number of parameters associated with this architecture is very large. Why? Because the 10 to the power 4 into 10 to the power 6 means 10 to the power 10 number of weights plus 10 to the power 6 bias, then plus 10 to the power 6 into 26 weights, and then again 26 number of parameters bias. So it involves lot of parameters. So you require more computation time. You require more number of training samples to learn the relationship between input and output. So what is the way that we can reduce this number of parameters? So then there was another piece of work which talks about the difference between shallow architecture and deep architecture. So I explain let's say like this, that instead of only one hidden layer, if I choose two hidden layers between this, then by choosing lesser number of hidden layers, still you can learn relationship between input and output. And instead of two hidden layers, if you choose three, then further the number of requirements of nodes will decrease and your number of connection also will further get decrease. So by employing more number of hidden layers, we can decrease the number of connections which we want to learn for a given problem. So although this research work was there prior to 2000, but still most of the research were using only one hidden layer or two hidden layers. Then the question is why they were using only one hidden layer or two hidden layers. So I'll tell you briefly, because we were using back propagation algorithm for changing the weights using gradient descent method, and it suffers from problem of vanishing gradient or exploding gradient problem. Okay, but then parallelly, at two different labs, people were working on deep learning, and then they were able to resolve that how we can develop deep learning models, which are actually we are able to implement. Okay, and you can see that as per MIT Technology Review, it is a world review. It was published in 2013. At that moment of time, it was said that deep learning is one of the, you can say, breakthrough technology among all science and technology development which has taken place. And now you can understand, we are talking about 2025. We can see that lot of development has taken place in deep learning. Many successful real-time applications has been developed using deep learning models. Okay, and because of this deep learning models, many Nobel Prize has been given this year. Okay, and we are talking about what is the development which is happening around. So let's see what is the difference between traditional machine learning or conventional machine learning and deep learning. In conventional machine learning approach, given the data, we used to extract relevant features. Either some experts should help us in telling what should be the features we should choose from this data, or we use some methods to extract features from the data. And once we represent a sample in terms of relevant set of features, then we were using some predictive model like multi-layer perceptron or support vector machine or Bayesian classifier or KNN or decision tree. Okay, so that was a traditional approach, that from the data, first learn relevant features, extract relevant features, then use those features and build decision model. But now when we are talking about deep learning model, we are saying this model block is like this, that it takes raw data and both feature learning and predictions, they are done in combo. Okay, they are integrated. They cannot be considered as a separate block. Means both are, you can say prediction and feature learning are done parallelly. Okay. So let's see this. I think many of us has played with the toys which was gifted by our parents, where we were given a toy box which contains blocks of many different colors, of different size and different shapes. Okay, and then we used to join them together in different ways, and we were able to obtain different kind of objects. So we were able to obtain butterfly or aeroplane or bird or helicopter or tank or your human, many kinds of, I think, objects we were able to build. But the building blocks were same. We were using a given set of blocks. So in deep learning model, the objective is that, let's say if you are given an image is represented in terms of a set of features. So what we are doing, that first from this image, we are able to learn basic features. And these basic features are nothing but, let's say, edges. Horizontal edge, vertical edge, you can say diagonal edges of different orientations. So we find out what are the different kind of edges present in this training set of images. Then we join them together to make different kind of shapes. We can make triangle, we can make circle, we can make square, we can make pentagon, hexagon, we can make nose, we can make eyebrows, we can make eyes, we can make chin, we can make lips. So, but how we are building? We are building those with the help of building block. Those are nothing but edges. So in deep learning, what you are going to see is that you are going to, let's say, given an input image, and from this image, first you learn basic level, low level features. Then you combine these low level features and get mid level features. Then you combine mid level features and get high level features. And then you combine these high level features to make different kind of objects. So that's what happens. But how you can extract these edges? How you can get low level features? How you can get mid level features? How you can get high level features? So for this, the first architecture which was suggested long time back is your linear architecture. This was the first successful architecture which was suggested. And in this, what is happening? You are given an image and your objective is to classify this image. And let's say you have 10 kinds of characters. You want to differentiate these 10 kind of characters. So first what you do from this image, using convolution filter, you learn features. So each convolution filter learn one particular feature associated with the image. So let's say we use 6 different convolution filter. So we learn 6 kind of features associated with the image. And let's assume that after applying convolution a filter of size 5 by 5, my output of this feature map is 28 by 28. So my original image was of size 32 by 32. So this is total. There are 1024 pixels. But after using this 6 convolution filter, we are getting 6 feature map and each is of size 28 by 28. So you find that the number of features which we are getting is much, much more than what is the number of features associated with the image. So what is the way that from these feature maps, we reduce the size of the feature maps and get relevant features. So for this, we apply pooling. So what we do in pooling? So we divide each feature map into many blocks, and from each block, we retain only one feature. So let's say I divide this image into a block of size 2 by 2. And from each 2 by 2 block, I get one feature. So 28 by 28 size image can be broken up into 14 into 14 blocks. So I will get 14 by 14 with 196 features I'll get from one feature maps. So I'll get this 6 feature maps, each associated with 14 by 14 features. Then again, we can combine these low level features to get mid level features. And for this, what we can do, again, we do convolution so that we can combine these low level features to obtain mid level features. Okay, and let's say we use 16 convolution filter, each of size 5 by 5. And so we will be getting feature map of size 14 by 14. Okay, and there are 16 such feature maps. And to further reduce the number of features and retain relevant features, we again use, say, pooling. And let's say it will reduce each block of size 2 by 2 to only one feature. So that's why we will get this each feature map, which was associated with the size of 10 by 10, can be of size 5 by 5. So let's say we learned low features, then now we have learned mid-level features. Now from this mid-level features, we can, let's say, high-level features. So again, we apply a convolution filter. And let's say we apply 120 convolution filters. And each of this convolution filter, let's say, give one feature. So I now associate an image with 120 features. And each of these features, we assume that this will be relevant. And then you think about this is a multi-layer perceptron where there are 120 features, there are 84 nodes at this layer, there are 10 nodes at output layer. Every node of this C5 layer is connected to every node of F6 layer, and every node of F6 layer is connected to every node of output layer. So initially, I don't know what type of filters I should have, convolution filters. What should be these weights? So what we do in convolutional neural network, you start with the random weights of the convolution filter. You start with the random weights of this network. You give the input data, you get the output. And if the output is different from target output, you change the weights. So again, you use gradient descent method or one of the variant of gradient descent method, say stochastic gradient descent method, or you talk about RProp, or you talk about Adam optimizer, and there are many more. Okay. So I hope I have explained you. Okay. So what you do in convolution, I think for those who are not aware of what is convolution, so I'm explaining that let's say you have an image, this is an image, and this is a filter. What we do, I bring this filter, I place it here, so it covers a space of 3 by 3 size, and I find out a dot product of this. So this will give me a value 3. I move this filter by one column right. Again, I find out dot product. It gives -1. Again, I move. And in this way, I can find out what is the output I'm getting after convolution of image with a filter. So you can see that in this image, there is a one pattern. This is a pattern. This is a pattern. And this pattern is associated with the value 3. And this is also 3. So at the same position, there is a pattern. Both of them are giving the same value. And this is the maximum value associated with this feature map. So if now I do pooling and I divide this into many blocks of size 2 by 2, and I retain, let's say, maximum. So I am able to capture that pattern, which is associated with 3. This is 0. There is no pattern, 3. So you find that in this way, you can see that this feature map can capture one kind of pattern. Okay, so now you see that in this image, I have applied your same max pooling and I'm getting this. So can you see that both of them give the same set of objects present in the image? So if also bird. Tree is there, here is also tree. Background remains the same. So we are not losing any relevant information. Only thing is that now we are representing with a reduced set of features. Okay. And I think you also must be knowing that what is softmax layer and then how to compute error. So error can be computed in many different ways. Most commonly, your error is computed in terms of cross entropy loss function. Okay. All right. So, but if you see it carefully, the number of parameters, how many parameters are involved with convolutional neural network, and for solving same problem, if I would have used neural network, how many parameters are involved? You will find that the number of parameters associated with the convolutional neural network are too few in comparison to the similar size artificial neural network. So they are easier to train. And the reason behind is that why we were able to reduce the number of features, because in the image, lot of redundancies are associated. Okay. And so when you are saying that a lot of redundancies are there, these patterns are occurring in the image at different places, same pattern, I can learn the same pattern with one filter. And this filter takes only lesser number of parameters. Okay. All right. So then after the success of this LeanNet, then people started building up more deep architecture. So if you talk about this architecture, we talk about this is associated with 1, 2, 3, 4, 5. We say it is your 5-layer architecture. Because pooling layer, we don't consider to be a layer, because pooling layer does not involve any parameters. So then people develop your LXNet architecture. And in comparison to LeanNet architecture, it was, you can see it was 8-layer architecture. So the depth is more. Now it was working on bigger size image. Now you see that the input image size is 224 by 224. Okay, and then what is the other difference? The other difference can be that for the first time they have used a new activation function, that is ReLU activation function. Because because of sigmoid function also, the network suffers from the problem of vanishing gradient. Okay, your sigmoid also creates a problem. Okay, but ReLU function helps us to reduce the effect of vanishing gradient. So, but again, then there was development that for to increase further depth. Okay, so more will be the depth. It will create a problem of vanishing gradient. So ResNet architecture was suggested. So for the first time, it has given the concept of skip connection. And you can see through this diagram that if you develop two architectures, okay, and let's say one architecture is your plain architecture, 18-layer architecture without a skip connection. Another deep learning architecture with 34 layers shown by red color. And the first one was showing with blue color. You see that as we go for higher iterations, you find that the error associated with deep architecture, that is your 34-layer architecture, is more in comparison to 18-layer architecture. Although we expected by increasing the depth of the architecture, our errors should decrease. But if instead of this, we have used two different ResNet architecture, one with ResNet 18, another your ResNet 34. Okay, means 18-layer ResNet architecture and 34-layer ResNet architecture, we could see reverse phenomenon. That you can see that now with the increase in depth of the architecture, your error is decreasing. And that was the big breakthrough of the use of residual connections or skip connections. Okay. All right. Now let's see that we talked about convolutional neural networks. Now we are going to talk about transformers. Why we are going to learn transformers? Why these days people are talking about transformers? So I am taking two broad problems. One problem of machine translation means you are translating from one language to another language, say English to German translation. And these are showing performance that when we have used your convolutional neural network based architecture, first one is your recurrent neural network based architecture. These two are your convolutional neural network architecture, and this is your transformer based machine translation. Can you see that the performance achieved with transformer based method outperform convolutional neural network based and recurrent neural network based architecture? Similarly, for image classification, for different your data sets, you have many data sets, ImageNet, Real, CIFAR 10, CIFAR 100, pets, flowers. So on all of this column is showing that the best state of art, you can say convolutional neural network architecture performance achieved. So ImageNet performance best was 88.5, but your Vision transformer is giving 88.55. This is giving 90.55 on ImageNet Real, while Vision transformer is giving 90.72. So can you see that we are able to outperform the best performance achieved by state-of-art convolutional neural network based architecture, okay, with the help of your transformer based methods. So now let's understand what is your Vision transformer. And for understanding transformer, how transformer is different from convolutional neural network architecture, because transformer main component is your that you are talking about attention, means long range attention. So let's understand what do you mean by attention. Say you are speaking a sentence, C is eating a green apple. And now you want to see that which word is associated with other words. Means you want to understand the context. So when you are talking about apple, what kind of apple? Green apple. Can you see that between these two, there is, you can say, high correlation. Okay, these two are related in much more. Okay, so means then I should be as giving some more weights to green and apple kind of tokens if these two words occur together. While you see green. So eating green, what is eating green? Okay, so this does not give that many, but green leaves, green apple. So there is some kind of a relationship, but this relationship is lower in comparison to the relationship between these two tokens, green and apple. So how can we capture the context, whether there is some context associated between the two tokens? And if there is, it is associated, what kind of, whether it is low attention or it is your high attention, it is your mid attention, means there should be some numerical value we should be able to associate to know your context associated between two tokens. And that was the first time when you talk about LSTM, that also captures some kind of context, or that also capture attention, but it does not involve long range. In the case of transformer, so when we are saying attention is one of the component, so what is attention? Attention is a method of gathering relevant contextual information. And how you are able to get this? So you are saying the transformer is actually a neural network, and that relies mainly on learning this attention associated between these tokens. Okay, and it has been seen that state of art models today in across all domains. You talk about text, you talk about your video, you talk about images, you talk about some other kind of data sets. Now these days, everyone is trying to incorporate transformer based model. So let's see what is your transformer. So I'll explain first for sequential data. Okay, so when you have a sequence of data, so let's say you have a sentence or you have one-dimensional signal. So I can break this sentence into many tokens. So you say a sequence of tokens. Okay, now in the transformer, in original work, it involves two components, encoder and decoder. But since we are specific, Vision transformer utilizes only encoder part. So I'll be talking about only encoder component. So what transformer is this encoder part is doing? You are taking some input, but machine does not understand text data. So this text data has to be represented in terms of numerical values so that machine can understand. So I want to transform, I want to represent these tokens in terms of some numerical values. So we do some kind of embedding, word embedding. Okay. So similar kind of words will have values or feature vector associated, where they are less different. But if there are two tokens which are very dissimilar, so in this transform space, they should be at larger distance. They should be separated by a larger distance. So using this thinking, so let's say there is a way by which you can transform these tokens into some another domain where similar words are mapped in the domain which are near to each other, while dissimilar tokens should be mapped, which should be separated by a larger distance. Okay. So I told you that actually transformer, which was originally suggested by Vaswani, it was involving another component also decoder, but for vision transfer, we don't require, so I'll not explain this part. So you will see that when you talk about transformer, okay, means basically after converting this input to some meaningful representation, we also need positional embedding. We'll understand what is positional embedding. Together means word embedding, positional embedding, these two will be used and will be given to this blocks. And this black box has two main component, and this component we say it's your attention block, while this network is your multi-layer perceptron. So I think we have already learned what is your multi-layer perceptron. So I will not talk about this in detail. So, but when I talk about this block, we are using the word multi-head attention. So what is multi-head? What is attention? Let's try to understand. So I said that machine does not understand words, say I eat mango or Ram eat mango. So we have to represent this into some numerical number. So I'm saying for this, you need to do encoding. That how I should convert these into first some numerical value. And after getting those numerical representation, then I will use this network for encoding. And what it will do? First, it will see the context associated between various tokens. And after we learn this relationship, and based on this, I get some output, and those outputs are utilized further by, say, multi-layer perceptron to represent into some meaningful representation. So we can use this block multiple times, okay? And can have deep layers of this so that my input is converted into a set of meaningful representation, and that can be used finally for classification or for some other kind of recognition. So let's understand self-attention. Okay, what is self-attention? So let's say you are given an input sequence X. Okay. So if you are given an input sequence X, so corresponding to this X, I will get some query Q. And for the same X, I would like to get a value K, that is key. And for the same X, I'll map it to another vector, that is V, using some linear transform. So I'm saying X is converted to Q, X is converted to K, and X is converted to V. So as we do query on our Google, that when we type certain query, it gives you a certain kind of meaningful output. So similarly, you can think like this, that you are given a query Q. You would like to see that Q among the given set. What is the, you can say, similarity between query Q and key K? So this can be computed by, let's say, Q into K transpose. But Q is associated with some feature vector, K is associated with some feature vector. If the dimension of this feature vector is large, this can have larger value. If the dimension of this feature vector is less, then this value can be less. So we want that this should not take a very large value. So we want to normalize. So what we do, based on what is the dimension associated with the feature vector, I divide by square root of with that dimension. So this will tell me some kind of, this will help me to get the weights. And I use those weights and multiply by values to get a new output. So let's see with the help of some example. So let's say you have input sequence X. So let's say there are two sequence. One input is thinking, another input is machine. So let's say I have input X1 and X2. I have embedded this. I now say the thinking is represented in terms of this feature vector of dimension 1 by 4, and machine is represented in terms of a feature vector of size 1 by 4. So what I said, that we project X into Q, K, and V. So how we do it? So let's say there is a matrix WQ and its size is 4 by 3. So if I multiply this X1, okay, 1 by 4 into 4 by 3, what I will get? I'll get a vector of size 1 by 3. So we are saying we are projecting X1 to Q through this matrix WQ. So this is your transformation matrix which transform X1 to Q1. Similarly, this is another matrix which transform X1 to K1. And this is another matrix which helps you to transform X1 into V1. So we are able to get for X1, I were able to get Q1, K1, V1. Let's say for similarly X2, we can get Q2, K2, and V2. So after getting this, what we are doing is find out. What was the formula? I compute Q into K transpose. So this is Q. So one is Q1, another is, so I compute Q1 into K1. And let's say this value is 112. And similarly, I compute Q1 into K2. Let's say this value is 96. So can you see that these two values are different? So I said I divide by dimension. So let's say the dimension d under root dk is equal to 8. So if I divide 112 by 8, what you get? 14. Well, what if you divide 96 by 8, what you get is 12. Now from these values, I use softmax function. So what is softmax function? What will we do? Exponential of 14 divided by exponential of 14 plus exponential of 12. This will give you 0.88. While for 12, it is exponential of 12 upon exponential of 12 plus exponential of 14. So this will give you 0.12. So can you see that you are saying that for this, what is the weight I should associate? I said there are two weights. One is your 0.88, another is your 0.12. So what I do, I compute 0.88 into V1 and I get this new value. I compute 0.12 into V2, I get this new V2. And now I add this V1 and V2 to get Z1. So what you are saying that I'm able to get what is the representation of my X1 in another terms, that is your Z1. So X1 is transformed to Z1 and similarly X2 can also be transformed into Z2. So I am able to encode my X1, X2 into another feature representation, which we say Z1, Z2. Okay. So now let's say if I represent this is in a matrix form so that things are little simpler. So I had two X1, X2. This was WQ is same. I apply this, I get two Qs, Q1, Q2. Similarly, I get K1, K2. Similarly, I get V1, V2. So how I utilize this Q, K, V? So using this Q into K transpose, the size of Q is 2 by 3. The size of K is 2 by 3. If I take transpose, so this will be your 3 by 2. So 2 by 3 into 3 by 2 is 2 by 2. So I get a matrix 2 by 2. And then I divide by square root of dk. Okay, some dimension. What is the dimensionality associated with this? Okay, and I get some values. And now these are weights. So I'll get weights. So I'm going to associate those weights with your V and I'll be able to get a new feature vector that is Z1 and Z2. Can you see that some of them are talking? Hello. Can you ask them to mute? Okay. So can you see that how we are able to transform input X into Z? So you have X1, X2, I'm converting into Z1, Z2. So you think about, you have n samples, x1, x2, x3, xn. What I will get? I'll get Z1, Z2, Z3, Zn. Okay, so there is a way by which we will be able to transform. Then you have used, so this is with the help of one head. But when we are saying multi-head, what do you mean by multi-head? For the same input, I want to project, I want to learn a different representation. So let's say I learn feature with the help of one set of WQ, WK, WV. So I can get Z0. This is through one head. Using another set of projection metrics, I get Z1. With the help of another set of metrics associated with QKV, I can get another representation Z7. So I'm using 8 heads, and each head is giving, using, it is capture you can say relationship, context, and using that context, you are assigning appropriate weights. So we are encoding the input data. One in encoding is Z0, another is encoding is Z1, another encoding is Z7. So we are getting different encoding. But now we want to combine these different encoding with the help of multi-layer perceptron to get one compact representation. So this you can think about. These are the outputs of multi-heads. Then we are using here your multi-layer perceptron. This multi-layer perceptron is again a set of weights. Okay, so you see that in this case, if you combine, so the size of this is 2 by 3. So if you concatenate Z0, Z1, Z7, so how many such blocks we are concatenating? 8. The size will be 2 by 14. So we are representing by combining this concatenation, we are getting your matrix of size 2 by 24. And now if you use projection matrix of 24 by 4, so I am able to convert into a representation of size 2 by 4. Okay, so there is a way by which we can convert a given representation into some another. So this what is happening. You have some word embedding. Through that word embedding, for a given WQ, WV, WK, we learn one representation. From another representation, we learn another way. So let's say there are H heads. Each head will compute your new representation. So now I concatenate all these representation. Can you see this? We concatenate this all representation, and then we are linearly combining or linearly projecting through another transformation matrix. So that will be the output as a encoded version. So I explain without positional encoding. But what is the role of positional encoding? So see, if you have a sentence Ram eat mango and eat mango Ram. So can you see that the context are different here? So how you feel that this Ram eat and eat Ram, so what kind of weight should be associated when you have eat, after eat you are getting Ram. While if you are getting eat after Ram, then what should be the weight associated? Okay, but if you consider as a set, then set of 3 words, and this is also a set of 3 words. So if I associated one value with each word, then we lost the context. We don't know where this eat is occurring, where in this sentence. And to capture this, there are many ways by which we can capture where is eat in this sentence. Where is eat here in this sentence? Okay, and there is a way, and one of the simple ways that I can use sine and cosine function for associating a position value associated with each token. Okay, so I'll explain this with the help of example. Let's say I want, okay, to represent this. What is the encoding of RAM? Let's say encoding of RAM is in word embedding is 0 0.1, 0 0.2, 0 0.3, 0 0.4. And encoding of EAT is 0 0.5, 0 0.6, 0 0.7, 0 0.8. And encoding of Mango is 0.9, 1, 1.1, 1.2. Let's simplicity. Okay, so let's say this is the word embedding of these three words. But what is the positional embedding? So in this positional embedding, so you find in that this when you are talking about these for position 0, okay. So I can compute that what is the position of this RAM, okay, here. So you see that you use this value. I'm getting this is 0, this is 1, this is 0, this is 1. So I'm saying the positional embedding for position 0 word is your 0 1 0 1. So for say RAM, it is your 0 1 0 1. While for RAM, my word embedding is this. So now similarly, let's say for second word eat, let's say the position embedding is giving value this. Let's say for word 2, let's say position embedding is value giving value this. So now what is the net input that is going? So for let's say the or cat or set, or for the ram or eat or mango, what I do, I add word embedding with position embedding, and after adding we can get a new embedding, and that will go as an input to the network. Okay, so if you remember, the encoding of the word was 0 0.1, 0 0.2, 0 0.3, 0.4, while position embedding is 0 1 0 1. So if you add them together, so this will give you what is the embedding of the. Similarly, we can find out what is the embedding of cat or sat, or similarly what ram or eat or mango. Okay, so you see that we are able to get final embedding for ram, eat, and mango is this. Okay, and if you talk about mango eat ram, then this representation will be different. So you see that in transformer, we talked about that first is that given tokens, you should be able to get word embedding. Your position embedding is important to understand the context between the two tokens. So we combine them together, we learn a new embedding, and using this new embedding, I'll be able to get my output as a encoding. And further, I can use this block again. I can have higher level of complex encoding. And this is the original architecture used by Vaswani for your machine translation. Okay, so this has encoder component and decoder component, but due to limitation of time, I will not explain this. So now, what are the advantages of transformer? So the advantage is that each token can have access to all other tokens in the sequence, but it learns a relationship between every pair of the tokens. Okay, and this can be parallelizable. We can do this in parallelly. Okay, and this has shown empirically has shown that it performs better excellent information at higher scale. So when experiments were performed on natural language models, it has been seen that this transformer learning perform better at higher scale. Okay, so you find that your test loss decreases when we are going to use larger amount of compute for training. The performance increase when you use more size of data size, and performance increase when the number of parameters involved in the network is more. Okay. But what is the weakness? The weakness is if there are n tokens, so you have to learn relation between every pair of tokens. So means you are learning approximately n square relation, n into n minus 1. Okay, so every token has to be find out what is the context with other n minus 1. So it is your n into n minus 1. So order is n square. Okay, so this is your quadratic time complexity algorithm. Okay, so transformers. What is the other disadvantage? The other disadvantage is that these powerful language models are extremely expensive. And the third is that transformer models overfit easily on smaller data sets. So if you really want that better performance of transformer, then you have to use larger size data sets. Okay. Now, let's go beyond languages. We are interested in vision transformer. So let's say we want to use transformer for vision problem. So we see that CNN are good for vision. Okay. We have seen that transformer are the choice of architecture for NLP. Okay. So how we can use some of the, you can say married some of the advantages of transformers in our architecture so that we improve the performance. Okay. So then what has been done is that there are numerous architecture has been suggested which has by incorporating self-attention in CNN architecture. So there are many research work where they have seen that by incorporating attention mechanism in the CNN architecture, performance improve. But many of them are have disadvantage because they have limited attention they are able to capture. So let's see how transformers are actually used. Okay, so let's think about that you have a image and the size of the image is 224 by 224. So how many pixels you have? Approximately 50,000. Means then how many pairs of relationships you have to capture? 50,000 into 50,000. It's too big. Means if you want to learn context between every pair of pixels, then it requires a lot of computation time. Okay, so it has associated with quadratic complexity, so it has a problem. So then what is decided? So in Visa transformer, what was suggested is that you divide the image into many patches. And think about this, each patch is one token. So in this case, how many tokens you have? You have 9 tokens. So can you represent each token in terms of some feature vector? And this feature, in this case, there is no problem. You don't have to learn something because you can associate what is the intensity values associated with this set of pixels. So let's say if this block is of size 16 by 16, so means your 256 pixel values will be associated, and I can represent each patch with a feature vector of 256. So I'm saying each patch is represented in terms of a row vector of size 1 by 256. Now it has become similar to what we were thinking about earlier. From in NLP problem, we were learning each token a word embedding. I'm saying here this token can be represented in terms of intensity values associated with each patch. And assuming that the size of this P patch is 16 by 16, I'm saying that each patch can be represented by a feature vector of size 1 by 256. So I have these 9 patch. And now I want to learn what is the context of this patch with this patch, this patch with this patch. So now you have to see only 9 square context approximately. Okay. And so you have seen that how to do it. So we have converted this patch into a flattened patch. So each one will be of size 1 by 256. We can also consider position embedding. And now we combine this your actual embedding with the position patch embedding with position embedding. And now these will go to this transfer encoder. What is this transfer encoder? This transfer encoder consists of many heads. What each head does? Each head tries to represent my data in terms of a new representation. So if I am using H heads, so I'll be learning H different representation. I concatenate this H representation, and then you use multi-layer perceptron to learn a new representation, and then this new representation can be used for classification. So that's how people are able to use modified transformer, which was actually suggested for NLP for vision problem. But still, if you have a big size image and you are going to represent only in this 9 patch, you may lose many information. So what is the way? How to find out right number of patches? So what is another word suggested that we think about hybrid approach? Say we use resident architecture. So let's say we use 50-layer resident architecture to learn a new representation of the image. And so that now this will tell you how many patches which you have. And now we use these patches for this vision transformer to learn classification problem, solving classification problem. Okay, so it has been seen. So let's say you have different kind of vision transformer models, and how we are differentiating, how many layers we are using. So if we are using less layer, we say base model. We're using large number of layers, we're saying huge models, and in between, let's say we are talking about large models. Okay. So base models use 12-layer architecture, large layer use 24-layer architecture, huge layers used 32-layer architecture. And the parameters associated with them is you can see is a big difference. Okay, so let's say if I want to represent for notation, because I'll show you some kind of comparison. So ViT stands for vision transformer. L stands for that you are using large model. And what is the size of patch? You are saying the size of the patch is 16 by 16. Okay, so this is the notation, let's say we are using. So now let's see some of the experimental result. So it has been seen that if we are using a vision transformer, which is your Hughes vision transformer with the image patch size is 14 by 14, it is outperforming the performance with all state of art convolutional neural network based models. Okay. Similarly, let's say if I use another architecture, I think this is giving better performance with other. So vision transformers are effective at scales. Means that if you want to see better performance, then the data size that should be available for training should be large. The performance of vision transformer is not good when you get limited amount of data. So this has been shown with the help of example. So you are seeing that you are using different architecture. You are showing the comparison between the two. So ImageNet has lesser number of samples, while JFT has larger number of samples. And you can see that for smaller data sets, the performance of your uh, your ResNet architecture is better than your vision transformer based models. But when this data side has increased, so you can see that the performance of this ViT large is almost equivalent to your ResNet architecture. But when the size of the data set is much larger, you can see that the performance of your all this ViT architecture is much better than your ResNet architecture. Okay. So similarly, it has been seen that if you give more training time, so in that case, what is you can say the comparison in terms of your accuracy? Okay, and it has shown comparison between transformer based model and ResNet architecture and hybrid. So can you see that as you are giving more compute time, the performance of the hybrid model is coming out to be better, and definitely the performance of transformer is definitely much better than other models. Okay. So So definitely there is a paradigm shift in computer vision. Okay. So now there can be a question, do we still need convolutional neural network? You cannot say no. So if you have this problem where the data size is less, okay, you cannot use transformers. Okay. All right. And then the question is how we can extend this vision transformer for segmentation. So people are using vision transformer for segmentation also, because in segmentation or object detection, along with encoding part, you should have decoder part also. Okay, so we can have decoder part in the similar way to make this problem, this vision transformer suitable for segmentation and for object detection also. Now people have also utilized vision transformer for video processing. Because you will all know that when you talk about video, so video consists of a set of frames. So and each frame is a spatial data, and then as frame moves, we say it is your temporal data. So video data has two components. One is your spatial component, another is your temporal component. So people have suggested VIT, you can say vision transformer for video, vision transformer for video. Okay, and many models has been suggested. I am just talking about only few of them, where we talk about let's say all these frames are considered as different tokens. So we learn embedding from these tokens, and we also learn position embedding, and this will go to this block. But when you talk about this whole block, so basically in this encoding, so we are going to talk about three kinds of encoding. One is your factorized encoder, another your factorized self-attention, another your factorized dot product. So in your factorized encoder, first of all, from the data, we are trying to learn your spatial component, and then we learn temporal component details. While in factorized self-attention, what we do, we learn first spatial followed by temporal. This is one block. Output of this is again given to this block to learn your self-attention. And then for factorized dot product, we have to do it in conjunction. Okay, means these spatial and temporal data both has to be fused. Okay. So one kind of a way can be that what we can do, that you can combine this frame, all these frames. So this is one frame, this is another frame, this is another frame, and we can think about a one big image. We can think about this one big image, and where I divide this each image into many patches, where each one of them are saying, let's say x1, x2, x3, x4, xj plus 1. And so these will be represented as a token. So we know that how these tokens are changing with respect to time. Okay, so then this image can be given as an input to the vision transformer to analyze videos. I think I'll stop here. Okay, so there are many more things, but due to limitation of time, I will not talk about. So let's conclude. So what is transformer model? So what is transformer model? First, basically transformer models using many blocks of encoders, where each encoder consists of blocks consisting of self-attention and multi-layer perceptron. Okay. And second thing is that here we are assuming very few assumptions to build this model. We are trained, then you originally this transformer model was suggested for natural language processing. But now these transformer models are being many variants have been suggested. If in fact in NLP itself, okay, to improve it further, lots of variants have been suggested for transformer model for NLP. But now transformer models has been suggested for vision problem also. And here we think about that a set of pixel represents a token. Okay. To reduce the complexity associated with the transformer model, which involves quadratic complexity. And it has been observed that if the data size available for training is less, then the performance of transformer models is less than state of art performance achieved by convolutional neural network based model. Means convolutional neural network based models are superior when the data set is lesser in size. But when the data size is larger in size, then it has been seen that the performance of transformer-based model is better than convolutional neural network-based architecture. And the reason is this, because they are able to capture a context associated with the pixels associated in the images. And because of this reason, they are able to learn better features, and that's why they are able to perform better. I think with this, I'll stop here. I thought that let's have some time for question answers. Okay. Okay. So if you have any query, okay, you may ask. Okay.
It's a request to all participants, kindly raise your hands. And if you have any queries, you can write in the chat box as well.
Now it will be better if you allow them to ask. Huh? I think that will be better, huh? If it is possible. Huh?
Okay,
Okay.
sir. Okay, sure, sir. Sure.
It seems no query. Huh?
Hello, good evening, sir. Am I audible?
Yes, you are all audible.
Sir, actually, in my case, I'm having CSI data, that is channel state information.
Can you be little louder? Can you be little louder? Huh?
In my problem, I'm having the CSI data, that is channel state information between a transmitter and receiver, which is sequential time series.
Okay. Okay.
So, but my data set size is a little bit less. How can I tune a transformer model?
No, I will not suggest, don't use transformer, because transformer will give better performance only when the size of the data is large. So one way is that what you can do, you can augment the data. Okay. Is it fine?
Yes, sir. Initially, I was using LSTM. Now, probably how to use something.
You are using which, what we are using?
LSTM, sir.
LSTM. Okay. Okay.
Yeah. Now, I should augment data and try with the same LSTM, or I can go with transformer and after augmentation.
If you can generate larger data sets, then only you think about you are using transformer. Okay.
Yes, sir. Okay. Thank you.
Okay. Any more question?
Yes, sir. There is one question in chat box from Nadeep Kumar. We want to ask, sir, can we assemble two transformers model?
What I said, and the computation time associated with transform itself is very large. Okay. So if you you make ensemble of two or more transform models, don't you think that computation time will be further very large? Okay, so I will not suggest that you use ensemble of transformers. Okay. Is it fine?
Nadeep, are you in the meet? Okay, so we have another question in chat box from Dr. Kumud. What happens when we increase the number of heads to a very large value?
See, in terms of when you talk about algorithms, when the input size will increase, what will happen? Time complexity will increase. It is definitely it will be some function of number of heads. Okay. But sometimes considering very large number of heads also produce redundancy. Okay, so I think what can be an interesting research is that what should be the number of heads? What should be the optimal number of heads we should choose so that we learn more representation, but at the same time, we should not generate redundant representation. Are you getting my point? Okay.
Okay, thank you, sir. There is another question from D. Malde. How to mitigate the biases in the architecture level?
How to?
How to mitigate
Uh, uh,
mitigate the bias in the
uh.
architecture level?
So for this, it is important that you should have, since the number of weights involved are too many, so what is suggested that you use large number of training data. Okay. And see that in some way you use lesser number of parameters in the model. Simple, Mike. My simple question is this. If I have an equation, x plus y is equal to 2 and x minus y is equal to 0. Can you get the solution of x and y? Yes, I can get a unique solution. But if I'm saying x plus y is equal to 2, so how many possible solutions you have? Infinite. Okay. So if the number of parameters in the model will be too many and number of training samples will be less, then you may have large number of possible solutions. So on training data, you may learn one solution, but which may not be good for new test data. Is it fine?
Thank you, sir.
Hmm.
And then there is one more question from Souvik Majumdar, that
Hmm.
which is best approach using CNN and Vision Transformer?
I will say if you have large data sets, you definitely you have good compute available at your end, I will suggest you use Vision Transformer. Okay, but if you don't have large resource, you don't have enough data, in that case, I suggest you use CNN. But even in CNN also, you use CNN of less depth. Okay, architecture.
Okay, thank you so much, sir.
Hmm.
Hello, sir. Am I audible?
Hello.
Yes, you are audible,
Yes.
Yeah.
Rajkumar.
Yeah. First of all, thanks for this wonderful session. So I have a question. So how does a language translation app like Google Translate leverage transformers to accurately translate between languages?
Between?
Between languages.
So if you talk about actual work of Vaswani, okay, so it has two components. One component is encoder, and there is another component decoder. Okay, so initially, let's say for a given English sentence, I have a German sentence. Okay, and I have many such samples. Okay, so what I will do, I will give my English sentence as an input, and what should be the output of the machine? Corresponding German sentence. Okay, so there will be some kind of encoding and there will be some kind of decoding that will happen. And it involves some parameters in modeling, encoding and decoding. So for a given input, I am not getting corresponding German output. It means my network parameters are not good enough. So what I will do? I'll change the weights. Okay, so I have many such samples. So through these many samples, I will be able to see that for a given input, I'm getting corresponding output or not. For a given English sentence, I'm getting corresponding German sentence or not. So if I'm able to achieve a set of weights And what are these weights? These weights are nothing. See that when we are talking about Q, K, V, I am using some transformation matrix, WQ, WK, WV. Then I'm using WO. So all these weights we need to learn. So if you find that for a given sentence, I'm not getting correct translated sentence, I will change the weights. Is it fine? I think in this such less time, because to make you understand how decoder works, then you have to attend one again my at least 2 hour sessions. Okay. Okay.
So what role do positional encoding play in transformer model,
I have
and why
explained
are
with one simple
they
example.
necessary?
See, I'm talking about Ram eat mango. Okay. So one is, who is eating mango? Ram. Okay. Then yeah, can you see that eat mango? So there is some context. What is being eaten? Mango is being eaten. And now I write other way around. I write down mango eat Ram, although it does not have any meaning. Let's say this is a sentence. Mango eat Ram. So do you see that this the context of mango eat has changed? Okay. So, but if you consider this as a set, then ordering will not have any problem. But I want to see that eat mango is different from mango eat. Although it looks that they are near to each other, but eat mango context is definitely different from mango eat. So how to capture? So that next time when I translate into this, that they should give different representation. Means corresponding to eat mango, my representation should be different, and corresponding to mango eat, my representation should be different. All right. And that is captured only by positional encoding, so that it captures that these two words have occurred at what distance and where. Okay. Is it fine?
Yep. Thank you so much, sir.
Thank you so much, everyone, for your questions. Uh, a heartfelt thank you to Dr. R.K. Agrawal for your enlightening session on Vision Transformer model and its application. Your, your detailed insight into the practical application and real-world examples you shared have given us a deeper understanding the power of Vision Transformer in modern AI. We sincerely appreciate your time, expertise, and knowledge. Expertise and the knowledge you have imparted today. Thank you once again for an engaging and highly informative session. As we wrap up day 2 of this exciting journey into generative AI, I want to extend my heartfelt thanks to our esteemed speakers for their insightful sessions on training generative models and vision transformers. Their expertise has given us a deeper understanding of these powerful AI techniques and their real world applications. A big thank to all the participants for their enthusiasm and engagement throughout the session. Your questions and discussion make this FDP even more enriching. As we move forward, get ready for the insightful day 3. It's a request to all the participants kindly join us again tomorrow at 6 p.m. sharp, where we will explore adversarial training and dive into the nuts and bolts of Transformer. We look forward to see you all tomorrow. Until then, have a great evening and keep exploring the endless possibilities of generative AI. Thank you.
And once again, thanks to all of you, okay, for patient hearing.
Okay.
Okay.
Okay, sir. Okay, sir. Thanks for your nice talk. And also thanks for accepting our invitation in this FDP.
Always, you're always welcome. Always welcome.
Yes. Okay, sir. Thank you. Good night.
Okay. Good night. Good night. Good night.
And thanks to all participants also for attending and listening patiently during the day. Okay. Good night.
Okay, sir. Thank you.
Sir, good evening, sir.
Good evening, sir.
Yes.
Sir, can we
Yes.
get the feedback link, sir?
See, I told you, I wrote the group also. Feedback link will come on your portal at the last day.
Okay, sir. At,
So you can
AICT portal, sir?
Yes. You will
Okay,
get
okay.
feedback. You can write the feedback over your portal, and then your certificate will be generated when you fill the feedback. So you can do one thing. You have workshop schedule, so you can note it down in your you can take the print of schedule and you can note it down the feedback so that you can fill later, or you can put some in Excel file.
Okay, sir. Okay.
If you want to remember the things, so that it can be recalled. But anyway, we have arranged the best speakers for you. So
okay, sir.
please,
Okay.
you can fill the at the end. Okay,
Okay,
it is AICT generated. We cannot do anything.
Okay, sir. Okay, sir.
Okay, bye.
Thank you, sir. Very good session, sir. Very good informative session, sir.
You
Thank you.
will enjoy more. Okay. Bye. Bye.
It's a kind request to all participants. Kindly leave the meet. Our session has been over.